Welcome everybody. Part 1, a different approach for the twin prime theorem. My name is Manuel P. Rodriguez Velasco and I am a mechanical engineer. And this study was presented December 22, 2022 at the Polytechnic University of Puerto Rico to a group of professors of engineering and science and for an audience. Mathematicians like Gauss, Euler, Riemann have tried to solve the twin prime theorem. Really, a lot of mathematicians through history and actually have tried to solve it. So what I did different? First thing we gotta remember that we can't make equations to predict the next coming prime numbers. And that's one of the bigger hurdles that we have to solve the twin prime theorem. I found a symmetry in the prime numbers. That symmetry allowed me to analyze numbers at very big numbers, very far away, where computers cannot reach, because the symmetry holds everywhere. And with that symmetry, I was able to make some equations, and with that equations lead to other things and to other equations, and eventually solving the problem. So, but we're gonna see how I did it right now. So next slide gonna be about the sieve I constructed. So let's continue. We're gonna study the prime numbers by their cycles. All prime numbers have a cycle. I am dividing the cycles in tens. Here you have the cycle of 3. But first, you gotta remember that all prime numbers except 2 and 5, they end in 1, 3, 7, or 9. All the numbers, the last digit, gotta be one of those to be able to be a prime. It could be, it could be not. So the numbers that you see there on the tens are the 3, the 9, the 21, and the 27. The other numbers that ends in 1379 that are not there could be primes. Like in the 10 from 1 to 10, gotta be the 1 or the 7. In the 11 to 20, gotta be 11, 13, 17, 19. And in the 21 to 30, gotta be the 23 or the 29. Any of those could be a prime, but not necessarily. The tenth of the middle is what I call a ten full of primes, or a prime 10. If we repeat the cycle several times, the same sequence gonna be repeated. I show you. Here you have the cycle of 3 with 3 iterations. It is repeated 3 times. In this one will be 1, 2, and 3. You can see that they have the same arrangement of numbers and of tens. All those numbers that you see there won't be primes, except for the 3. So you can have here 21, 27, 33, 39, and here in the last one, 81, 87. All of them that ends in those numbers won't be primes ever in every cycle of 3 when they keep repeating. The other numbers could be prime, but not necessarily. That depends on the next cycles of the primes. So gonna come the cycle of 11, the cycle of 13, cycle of 17, and it could affect other numbers in the cycle of 3. So we will see that in a moment. Here you have the cycle of 7. And how you can see, it has also 4 numbers that they represent numbers that won't be primes in the iterations of 7. How I told you, in the cycle of 3, the 49 was to be a prime number. But the cycle of 7 has 7 times 7, 49, and is here. So that number won't be a prime. That's why we have to check all primes to be sure what is a prime and what is not. This is the cycle of 7 with 2 iterations. How you see, they have the same numbers in the same positions of the cycle. So for infinity, those numbers in that positions of the cycle won't be primes ever. Here you have the cycle of 3 and the cycle of 7 together. So now you can calculate prime numbers looking in the same way that we did before. Here, 23 and 29 will be primes because the numbers are not here, right? There is no 3, there is no 9. And here, the 53 and the 59 will be primes. But there are other cycles. The cycle of 11 is the next one. And in this 10, 11 times 11 is 121. So in the cycle of 3 and 7, 121 was to be a prime. But because it's coming the cycle of 11, won't be a prime anymore. So that's the difficulty of knowing which are the prime numbers. Because every time that comes a different prime, will have a different cycle, and we cannot predict which ones will stay as a prime and which ones not. So here we have the first cycle of 7 that starts, for example, with the cycle of 3 in the first 10 of 3 and the first 10 of 7. And now it's different. Here is the start of the cycle of 7, iteration number 2, and look, now it starts together with the second 10 of the cycle of 3. Here it starts with the first 10 of the cycle of 3. Here starts with the second 10. And in the next cycle of 7, that is here, it starts here. It starts together with the third 10 of the cycle of 3. So I saw that they were combining differently. Every 10 was having different combinations of different 10s of both cycles. And I realized that they were combining in all possible combinations of 10. All possible combinations of 10 without repeating until they form a new cycle. Here you have the cycle of 3 and the cycle of 7 overlapping each other. They go from 1 to 210. That's their minimum common multiple in tens. So because 3 times 7 is 21, that's the minimum common multiple times 10, 210. And how I said, they combine in all different combinations of tens without repeating until 210. So the first 10 of 3 with the first 10 of 7, the second of 3 with the second 10 of 7, the third 10 of 3 combines with the third 10 of 7, the first of 3 with the fourth 10 of 7, and so on. You see that there is no repeated combinations. You have first with first here, and there is no other one there. Okay, so all are different. You have here third of 3 with the fifth 10 of 7, and there is no other 10 with that combination. After they finish 210, then they're gonna start again the same cycle. I'm gonna start in first with first, second with second, because all cycles go to infinity, right? Um, let's continue. So we have some new terms. Here you have the prime 10. Prime 10 is a 10 that has no any number. When you merge cycles, they're gonna stay like it has no number. Here is the start of cycle 11. These are potential primes, 263 to 269, because there is no 3 and no 9 in the 260s 10. So that's how we're gonna call them potential primes. Are primes numbers that can be primes, but could be affected by other prime cycles. Here is this one, the 9 here, is a flip potential prime. When you have, for example, in the 3 and 7 cycle, you have no 9 there, but it comes the cycle of 11 and flips the 9, the 319. So that won't be a cycle anymore. So we say that it's being flipped. Overflip is here. Is when comes another cycle of another prime. So in the cycle of 3, it was already flipped, but now comes the cycle of 7 and it's overflip because that's repeating, and that will be important for later. Here we have this rectangle that represents all possible combinations between the merging of the cycle of 7 with the cycle of 3. So we have 3/10 of the cycle of 3 from 0 to 30, and from 0 to 70, 7/10 of the cycle of 7. And we can see that they're gonna make all combinations because you have here 1, 2, 3, 4, 5, 6, and the 7/10 of the cycle of 7, all combined with the first tenth of the cycle of 3 in this way, you see? 1, 2, 3, 4, 5th tenth, 6th tenth, 7th tenth of the cycle of 7, all with the first tenth of the cycle of 3. And this one, again, you have from 1 to 7/10 of the cycle of 7 in this way here. And here you have the 2/10 of the cycle of 3. And here you have the 3rd/10 of the cycle of 3. And from 1 to 3, 4/10 of the cycle of 7, 5, 6, 7/10 of the cycle of 7. This one here. So you have all possible combinations here. Okay? But in those combinations gonna appear in an order in the real number line, and this is the order they appear. This order represents like this here. They start here, you see, 1 1 1 2 2 2 3 3 1 1 2 2 3 3, and then combines the first tenth of the cycle of 3 with the 4/10 of the cycle of 7, the second with the 5th, the third with the 6th, and now comes here and it goes in diagonals, and from here starts here, and that's the order they're gonna appear in the real number line. And this one, and the last 3 is these 3 here, so we can check 1 5 2 6 3 7. Let's start here. That's gonna be the last 3, right? So, and that's gonna happen with the next cycles forming, because now you have this, and this gonna be here on top, and then the next cycle will be the 11 gonna be here. Sorry, this gonna be in the next rectangle here, up here, and here gonna be the cycle of 11, and then they're gonna combine always in all possible combinations. So all these tenths gonna combine from 0 to the length of the cycle, that is with this formula. In this case is 210, okay? So we have here the cycle of 3 and 7 together. This is the cycle of 3 and 7 because it's what we saw in the last slide, but now we put all the numbers in the same box, right? So this is the same box, and we can see that all these gonna be the multiples of 3 and the multiples of 7. What happens with when it comes another prime number? We're gonna see that. When it comes another prime number, we're gonna have again the box that this is the 210, the 21 tenths of the previous slide gonna be here, and we're gonna have the cycle of 11, that is the next prime number after 7. We're gonna have the 11 tens of the cycle of 11, and they're gonna combine also in diagonals. And from here, from 0 to 2310, that is the minimum common multiple of the cycle of 3, 7, and 11, we're gonna have all the combinations without repeating of the cycle of 3 and 7 combined with the cycle of 11. Okay? All combination without repeating until day. And when it comes the prime number 13, again, gonna happen the same. Gonna happen all combinations possible without repeating, but the length gonna be on the 30,000s, I think. 30,030. So let's continue. So now we're going to study the symmetry of the cycle of primes. The cycles we saw there, they are symmetric, and I'm going to show that this is a new approach. First of all, I have new variables and names, so you can familiarize with them. Pn is prime number not 1 to 5 or 5 unless specified. This is the cycle of prime n. Cycle of that prime alone. This is the sample. That is the cycle of 7. Of length Pm times 10. They will be the cycle of Pn1, 2 until n. All the primes you put there. The prime 1 will gonna be 3 always, and prime 2 gonna be 7. Okay. So you can keep adding primes to the cycle and merging in new cycles. Okay. This is the cycle from 3 to Pm, right? From prime number 1 to Pm. So this is an abbreviation of this here. So here we have the cycle of 3 and 7, and it's a symmetry. It has a symmetry prime 10 on the middle. All cycles gonna have a prime 10 on the middle, and it's complete symmetry. In the symmetry, the numbers in the table, the 1 is linked to the 9 and the 3 is linked to the 7. What does this mean? If we start from one corner, we have the 3, the 7, and the 9. So in the other corner, gonna be the 3 is linked to the 7, so gonna be a 7 in the other side. The 7 is linked to the 3, so gonna be a 3. And because there is a 9, gotta be a 1 in the other side. So we're gonna have 3, 7, and 1 here. You see? 1, 7, 3. So because it's this second one is a prime 10, by symmetry in the other side gonna be another prime 10. Just sign like this, because it's 1, 7. In the other side gonna be a 9 and a 3, because the 9 is linked to the 1 and the 3 is linked to the 7. So in the other side gonna be a 3 and a 9. You see it here? Now next one here, 1, 7. So in the other side gotta be a 3, 9. 3, 9 here. And 9 here gotta be a 1 in the other side. 1. 3, 9 here gotta be 1, 7 here. 3, 9, 1, 7 here. And the 3 here gotta be in the other side, a 7, right? 7. 1, 7, 3, 9. 1, 3, 9. So must be 1, 7, 9 in the other side. 1, 7, 9. A prime 10 in the middle. So the symmetry goes from the center prime 10. All cycles gonna have a prime 10 in the middle. That's explain why the proof of that is in the paperwork, right? It's not here in the video, but everything is symmetry around the center line, around the symmetry center line. If you calculate the middle of all cycles, for example, the cycle of 3 and 7 is 210, you divide it by 2, and you will have 105. If you put those numbers in the middle here, they're gonna combine until the minimum common multiple until 210 until 0 when you expand it to the left and to the right. And that will happen with all combinations of prime cycles. You can keep combining and you will always have the symmetry line in the middle, and you will always be able to span to the minimum common multiple in this way and to zero in this way, and they're gonna fit perfectly. It doesn't matter how many prime cycles you have. That's why you're gonna have always a prime 10 on the middle. Here you have the cycle of 3 and 7, and from here starts the second iteration of the cycle of 3 and 7. So this is in the second row, right? So these are all the multiples. Here you have the tens, and underneath you have the prime numbers or potential prime numbers. Potential prime numbers because they are only inherit to the cycle of 3 and 7. It can come another prime numbers that will make the potential prime numbers not to be a prime number. So this we can see that in 121 is the multiple of 11 times 11. So at the square of the next prime number, we know that starts another cycle. Before that, we can know all the prime numbers, the composition of prime numbers. So because this is the cycle of 3 and 7, and the next prime numbers is number 11, we know that until the square of 11, we can know the composition of prime numbers. So until 121, we are able to know the composition of prime numbers. So this composition don't gonna change. After 121, it could change the composition. That will be this one. The numbers in red are potential prime numbers that are gonna stop being a prime number, that they're gonna be flipped, right? So, and the brown numbers are potential prime numbers that they will become prime numbers. So until 121, we can see that we can know the composition of prime numbers. Before that, only taking into account the cycle of 3 and 7. But when it comes the cycle of 11, we're gonna have the cycle of 3, 7, and 11 that gonna be until the square of the next prime number, that is 13. 13 to the square gonna be 169. So when we have the cycle of 3, 7, and 11 before 169, we're gonna know all the composition of prime numbers, only taking into account the cycle of 3, 7, and 11. So from here to there, I call it the real composition of prime numbers, and from the square of 11 and up is the unknown composition of prime numbers for the cycle of 3 and 7. So we gotta remember that at the square of the next prime number, we're gonna know the composition of prime numbers just taking into account the prime numbers of the cycle, just taking in account the cycle. For every cycle, there's gonna be a gap for every new cycle, and that gap gonna tell us the real composition of prime numbers in the real number line on that gap. So, for example, first we have this cycle Pm minus 4 in cycle, and we're gonna have this gap. This gap, all the composition of prime numbers in this cycle gonna be part of the real number line. And then gonna come the next cycle, Pm minus 3, and we're gonna have this gap. And that gap gonna map the real number line, that portion gonna be mapped at that cycle. Really, this and this gonna make only one cycle or both together, right? And then gonna come next prime number, and we're gonna have another gap. That's gonna be this one. And this gap gonna map this portion of the real number line. The composition of primes gonna be the composition of primes in that cycle, in that gap, right? We have here Pm plus 1, Pm. So for every new cycle, we're gonna have a gap that's gonna have the composition of prime numbers that gonna be the composition of prime numbers in the real number line. And this is the equation. The length of the gap gonna be the square of the next coming prime minus the actual prime that forms the cycle square also. And that's gonna give us the length of the gap and the composition of potential primes in that gap gonna become real prime numbers, okay? As we said in the last slide. So we're gonna be mapping a portion of the real number line for every new cycle form. So this is a very important part. And I want you to remember that we studied already that when the cycle of the number 3 combines with the cycle of prime number 7, they combine in all possible combinations of 10s. So you remember that. And that's important because if you have the cycle of 3 and the cycle of 7 here, right? And the cycle of 7, it has, let's say, number 7 here, a prime 10, number 1, a prime 10, it has a number 9, prime 10, and number 3. And the cycle of 3, it has 3 and a 9 in 1 10. Then it has a 10 with a prime 10. And then it has a 1 and a 7 in the other 10. So this gonna combine with all this. So the combinations of prime 10 is gonna be 1 here that's gonna combine with this one, with this one, and with this one, with the 3 prime 10s. So they're gonna combine like this gonna hit with this one combination, and this gonna hit with this one, and this gonna hit with this one. So you're gonna have 1 times 3 prime 10s. So you're gonna have 3 prime 10s because you're gonna multiply the prime 10s in one side, but the prime 10s in the other side, okay? Because they do all possible combinations, and all possible combinations gonna be 1 prime 10 here times 3 prime 10s in this side. As well, you're gonna have 3 and 9 gonna combine with every 10 of the cycle of 7. This prime 10 here of the cycle of 3 gonna combine with every prime 10 of the cycle of 7, every 10 of the cycle of 7, and the 10 of 1 and 7 gonna combine with every 10 of the cycle of 7. So we're gonna be looking at how combines the prime 10s. So this prime 10 gonna combine with these 3 prime 10s. Okay? And that's gonna happen again when comes next cycles. So we are reaching an equation, because if you multiply the prime tens in the coming cycle times the prime tens in the previous cycle, in the merge cycle already, you're gonna have the number of prime tens in the next coming cycle. And this is about this. Uh, so we can see here, if this is the prime time of the cycle of 3, gonna combine with the 3 of the cycle of 7, with the 3 prime times. And they're gonna form this 3 prime tens in the cycle of 3 and 7. It's gonna be the whole cycle of 3 and 7. And these 3 gonna combine with the next coming prime number, that is number 11. Number 11 is here. So the 7 prime tens of the cycle of 11, that goes from 1 to 110, gonna combine with the 3 prime times of the cycle of 3 and 7. So how many prime tens we're gonna have? 7 times 3, 21. And that's gonna happen when it comes to the cycle of 13. And we know that the number of prime tens in any cycle of a prime number, of a single prime number, how many prime tens gonna be in the cycle of 13? Gonna be 13 minus 4, gonna be 9. And in the cycle of 17, gonna be 17 minus 4, gonna be 13. Okay, so we are reaching an equation, a very, very important equation. That is that the number of prime tens in every new cycle is equal to the number of prime tens in the previous cycles times the new prime number minus 4. So let's continue. So we here again. This is the cycle of 11, and it has how many? 1, 2, 3, 4, 5, 6, and 7. When it comes to the cycle of 13, gonna have 13 minus 4, gonna have 9. We have now an equation. So here we have some new equations. S represents the number of prime tens in a cycle. L represents the length of the cycle. So S from P1 to Pn is the prime tens of the cycle P1 through Pn. And that's going to be equal to the prime tens of the previous cycle, P1 to Pn minus 1, times Pn minus 4. Because we already know that the number of prime tens in a single cycle of a prime number is the prime number minus 4. So if we have the number 7, the prime terms equals 7 minus 4. If we have number 17, equals 17 minus 4. That means that for example, the 7 gonna have one that ends in 7, a prime 10, one that ends in 1, prime 10, one that ends in 9, a prime 10. Wow, that 9 is beautiful. And one that ends in 3. So this what I refer to prime terms of the single cycle of the cycle of 7. Okay. And then we can continue with the other equations. Let me erase this. That will be that the prime tens per length of the cycle is S divided by L, right? So S divided by L equals this equation. Y, 1 divided, the first term gonna be 1 divided by 10 times P1. P1 is 3, because we know that the length of the cycle of 3 is 30, and it has only one prime 10. After that, we go with the equation of the corresponding prime number minus 4 divided by the prime number. All these terms down here are gonna be the length of the cycle, of the given cycle, and the numbers up here are gonna be the prime terms. So we already have one equations about prime numbers and about prime terms. So we have here again S minus 1 means the prime terms in the previous cycle, in the cycle minus 1. Okay, it's like this, this one, right? And L minus 1 also is the length of the previous cycle. Okay, so for any cycle will be the prime terms per length gonna be Pn minus 4 divided by Pn multiplied by the prime terms of the previous cycles divided by the prime terms of the, divided by the length of the previous cycle. So that equation is going to be important, and it starts little by little to evolve all these, going to lead to other things. So let's continue. So we're going to study now the combinations of non-prime terms, how they are formed, the non-prime terms. If we see the cycles of single prime numbers, this is a cycle of a single prime number, cycle of 11. This is a cycle of multiple prime numbers, that is 3 and 7, cycle of 3 and 7. But the cycles of single prime numbers, they're gonna have only 4, 1, 2, 3, and 4 tens with a number ended in 1, 3, 7, and 9. So we have 4 here, 1, 3, 7, and 9 for the cycle of 11. All the other ones are gonna be prime terms. So there are gonna be always only 4 non-prime terms in those cycles. So we can see that the 4 non-prime terms of the cycle of 11 gonna combine with the 21 tens of the cycle of 3 and 7, and they're gonna form 84, 21 times for 84 non-prime terms in the next cycle. So we have here also the combinations of prime tens of the cycle of 11 with the non-prime terms of the cycle of 3 and 7. They're gonna produce combinations of non-prime terms, right? So we're gonna have 7, 1, 2, 3, 4, 5, 6, 7 prime terms of the cycle of 11 times 18 prime terms of the cycle of 3 and 7, okay? That will produce combinations of non-prime terms. So for a total of 210 in both, for non-prime terms times 21, 84, plus 7 times 18, you will have a total of 210 non-prime terms combinations in the next cycle. Okay, so we can see that this is a beautiful process of making a space for everything, for all possible combinations of tens. That's how the composition of prime numbers are created. After this will come the cycle of 13 that will have 9 prime terms, and will happen again. We're gonna build another cycle, and that for every coming prime number. It's important to know that the length of the cycles, combination of cycles, every time you add the next prime number to merge another cycle, gonna grow very fast. But that doesn't matter too much. You can get in trillions very soon, but really the composition of primes and the proportion of primes doesn't change too much. So what happens every time that comes a new cycle, that you merge a new cycle with the previous one? You have here the cycle of 3 and 7, and when comes the new cycle, that will be the from 3 through 11, this is the triangle that is making. Really, it's a curve, right? But I put it like this. So you will have 11 times the cycle of 3 and 7 together with the cycle of 11 to form a new cycle, a new merge cycle. They're always gonna be symmetric. And look, now the length will be 2310 from 210, that was the previous one. And then gonna come another cycle, gonna come the until 13, right? 3 through 13, and you have it here. I'm gonna have 13 times the cycle from 3 through 11. 13 times 1, 2, 3, 4, 5 until 13. I'm gonna have again a symmetry in the middle, and the length gonna grow exponentially, 30,030. We have here the iterations of a cycle. We have the cycle 1 through Pn, and here we have the first iteration, second iteration, third iteration. So we're gonna have prime numbers at the beginning always, but those prime numbers gonna make that these portions here, the one that is in yellow and the one in red, don't gonna have any prime numbers, because all these numbers gonna be multiples of the prime numbers that are here, and here they're gonna be multiples also of the prime numbers that are here. So in the end of the first iteration and the beginning and end of next iterations, we're gonna have a portion with no prime numbers always. For example, if we have the 3 and 7, when it ends in 210, we know that the 213 and 217 don't gonna be prime. So until 217, we won't have primes in that portion. And also in the end of the first iteration, we're gonna have prime numbers. The only ones that could be primes are the 9 here, okay, and the 1 here in each iteration. In those, here and here, at the end, the last number of each iteration, that the last digit ends in 9, the last one that the last digit ends in 9 is a potential prime that could be a prime and could be not a prime. And also the first number of each iteration, that the last digit is 1, could be a prime, could not be a prime, gonna be a potential prime for each one of the iterations, okay? We will know if they're gonna be primes or not when they fall in the gap of a cycle, and then there we will know if they are or they are not. So that's how we fit the saying that they're going to be always a growing part of known prime numbers, or portion with known prime numbers, right? So in mathematics, there is already proof that the portion with no prime numbers can grow all as big as we want. The only problem with that is that it's gonna be so far and far away to find those portions so big that we're gonna be able to converge the system, and that you will realize it later. Okay. So the symmetric cycles of primes, they are symmetric. They start at 0. The first number with last digit 1 and the last number ended in 9 on each iteration of any cycle is always a potential prime. Always a prime 10 in the middle. There is always a pair of all the cycles that describes the real composition of prime numbers. So now comes the prime tens theorem, a proposed solution for the twin primes theorem, proposed by myself, Manuel P. Rodriguez Velasco, mechanical engineer. So we're going to state that there is an infinite number of tens with 4 primes. So you can see that even the length of the cycles are growing very fast. This is in tens, right? The number of prime tens also grows exponentially. So you're going to have lots and lots of prime tens combining. You can see here the proportion of a gap to the length of the cycle in this table. You see how small gets the gap. That means that the gap is going to be a very tiny portion of the cycle as we go up in cycles. And also you have here the proportion of tens per tens of cycle. And they get very, very small. This tells you how big gotta be the cycle and how separate gotta be the prime terms from each other. It's so big the length of separation between prime terms. That's why computer can see this, right? Not yet. Here you have the equation for the gap length, is this one here, and two computations for the gap. One is for the cycle of 3 through 19, and the other one from the cycle of 3 through 29. Here the gap decreases a little bit, but really when you go up in prime numbers, it's going to be increasing and increasing. So there is an important tendency to stabilize and repeat cycles, and that's approaching zero change. Imagine you have an ideal full of prime terms cycle. This is like the cycle of 3, but all are prime terms. That's ideally. When that combines with another cycle, let's say this cycle here, you're gonna have repetitions of that same cycle, exact repetitions. In the merging process, that is what it will happen. Any cycle merged with an ideally all full 10 cycle will duplicate exact copies of the cycle. You can see that here. If we merge together an ideally cycle of 3 tens with the cycle of 7, you're gonna have this. Here you will have the 7, here you will have the prime 10, the 1, the same as in the cycle of 7. You're gonna have repetitions of the cycle of 7, 3 repetitions of the cycle of 7. So here we have a stabilization of cycles, and we made a new variable v for the proportion of duplicate. This means that this is the number of prime tens, okay, in the cycle of Pn divided by the number of tens in that cycle, okay? So as you can see, for 7 is 0.42, for 11 is 0.6, and when we have prime numbers so big as this one is 0.99999. So you're gonna start having cycles that have more and more prime tens, because you're gonna have always only 4 non-prime tens or any cycle of a single prime number, as you go up in prime numbers, the composition of the cycle gonna have so many prime tens and only 4 non-prime tens. So they approach to an ideally full of prime tens cycles. They approach this. So you're gonna have a lot of prime tens and then a number and then a lot of prime tens. And when you go up, the number of prime tens gonna be so huge, and you're gonna have always only 4 non-prime tens. So you see here the cycles of single primes. As we go up, we're gonna have more prime tens. It's the prime number minus 4. As we go infinity, we are approaching an ideally full of prime tens cycle. So as Pn goes to infinity, we approach to an ideally full of prime tens cycle. So we're going to make equations as we go to infinity. So the length of the new cycle will be the length of the previous cycle times Pn, right? So this is the equation. That's always like that. We know that already. We're going to represent the number of prime tens in cycles, right, with the variable s. So the prime tens from the prime number 3 to the prime number n, the cycle, 3 through n, will be represented by the variable s. You have it here. So number of prime tens in the new cycle will be the number of prime tens in the previous cycle times prime n minus 4. And you have the formula here. They are very simple equations, basic equations. For a prime n equal 13, this is an example, we will have the cycle from 3 through 11 times prime n minus 4, and that will be the amount of prime tens that we will have. The cycle of 3 through 11 has 21 prime tens times 13 minus 4, that is Pm minus 4, will be 189 prime tens. So we have here the equation of the prime tens on the cycle from 3 to Pn. 3 is prime number 1, right? So this is the equation. That is the prime tens of the previous cycles times Pm minus 4. When we go to infinity, we can get rid of this 4 because number is going to be so huge that we can make that approximation. So at the end, we will have this as the equation of prime tens per cycle for every new cycle forming. And here we have the equation of the length for every new cycle forming, that is the length of the previous cycle times Pn. When we make the proportion of prime tens per length of cycle, we divide this equation divided by this equation, this divided by this, and we have it here. As you can see, on top and on bottom of the equation, they are multiplied by Pm. So as new cycles are formed, the proportion of prime tens per length in the cycles approaches a constant as Pn goes to infinity. This means that the prime tens approach a constant distribution in the cycles as Pn goes to infinity, with a little increase in the distance between prime tens for new cycles forming. Because the equation of proportion of prime tens to the length of the cycles always is from 0 to the length, the portion that had a bigger rate of change of prime tens per length of cycle will get smaller and smaller until we approach a closer to a constant proportion of prime tens as we go to infinity. This next slide is for you to understand how the prime terms get apart, they get separated. We're going to start with the cycle of 3 and 7. If you remember, the cycle of 3 and 7 has 3 prime terms. These lines here are the 3 prime terms of the cycle of 3 and 7. And this is the length, 210. So when the new cycle comes, when comes the cycle of 11, we're going to have a length of 2310. And we're going to have 11 repetitions of the cycle of 3 and 7, but with the flips of the produced by the prime number 11. So here you have all the repetitions is 11 times this, but I put the middle prime time, this one, I put it like bigger than the prime times of the sides, right? So you see it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that's the sketch of the cycle of 3 through 11, but we haven't done the flips produced by the prime number 11 yet. Let's continue next slide. So now comes the tricky part. When the cycle of 11 comes and merges with the cycle of 3 and 7, 11 of the prime tens are flipped. They are with the cycle represented with cycle here. In the first iteration of the cycle of 3 through 11, they are flip 11 of them. In the next iterations, gonna flip 12 of them. How we can calculate this? Remember that the cycle of 3 and 7 have 3 prime terms, okay? So times 11 tens is equal to 33 prime terms that we're gonna have, that are all here, all of these ones. But of that 11, of these 11 here, 4 of them are non-prime terms. So really 7 gonna stay as prime terms. So we're gonna have 3 times 7 equal 21 prime terms, really. Okay? And the ones that gonna be flipped is 3 times the 4 tenths of 11 that are not prime terms, and that equals to 12 that gonna be flipped. So we're gonna have 12 of them that gonna be flipped. But we see only 11 flip in the first iteration, because the 11, the prime number 11 is here in the first prime term. And because 11 is the first multiple of 11, but continues to be a prime term, then don't gonna be flipped in the first iteration. It's gonna be flipped in next iterations. So really only 11 of them gonna be flipped. After they are flipped, we're gonna have this here. This gonna be the prime tens of the cycle from 3 through 11. And every coming iteration of the next uh, um, every coming iteration gonna be repetitions of this one, except this here, this prime 10 gonna be flipped in the second one, so this don't gonna be repeated. This is the first prime 10, the prime 10 of 11 to 20, 10, the 10 of 11 to 20 there. So all gonna repeat it, but you see now how prime tens are separated, how they get apart from each other, because here we see that they have the same distance, but the ones missing makes an increment in distance from one prime 10 to the other one. For example, here there is more distance, and here also, and from here to here there is more distance. Every flip of prime 10 gonna increase the distance between prime 10s. This is really because every new cycle is several repetitions of the previous one, repeating its composition as many times as units of the new prime number. There is no extra space generated at all because all are repetitions of previous cycles. All of them are multiple repetitions of the cycle of 3, and the cycle of 3 is always the same side. The increase of distance of prime tens and prime numbers is due to the flips generated by the continuous coming of prime numbers that forms the new main cycles. The main cycles is the main cycle. I didn't explain that yet, but is you have the cycle of 3 that merge with the 7, so you have the cycle of 3 and 7, and then comes the cycle of 11, so you have the cycle from 3 through 11, that's the new main cycle, and then comes the cycle of 13 that merges with the main cycle, and the main cycle gonna become the cycle from 3 through 13, and then it will come the cycle of 17 that will merge with the main cycle. So the main cycle gets more and more prime numbers in order, in ascending order, okay? All flips of every cycle of a given prime number Pn added to the main cycle are multiples of itself with bigger prime numbers. For example, the distance in flips for primes in the hundreds, like for the cycle of 101 that is merged with the main cycle, its first flip gonna be the square, 101 times 101. This is gonna be the first flip, and the second flip gonna be 101 times 103, because 103 is the next prime number. And if you subtract this one minus this one, the difference is 202. So that's the separation between flips. The smaller separation, because the smaller separation is of a difference of 2 between prime numbers. But in the thousands, look, 10,007 and 10,009, this is going to be one of the flips and the second of the flips. Already the difference in flips is of 20,000, 20,014. And this is important because as we go up, the flip's gonna be far and far away. That's one of the factors that gonna make the prime times approach a constant in per length. Yeah, a lot of the people will say, "Wow, how they gonna be constant?" Because if the separation with no prime numbers can get bigger and bigger. Yeah, it gets bigger and bigger, the separation with no prime numbers, but does it exponentially. There is a moment that you are multiplying for so big numbers to find one more, two more digits without prime numbers, that really there is a convergence there. Okay, it's difficult to think about it, but you gotta study the system really well and realize that the parts with no prime numbers, they come so far away, and as you go up, it goes exponentially farther away. Those portions are the beginning and the end of the iterations of the new cycles forming. Okay, with a minimum difference of 2 between prime numbers, the minimum gap is this equation. If we simplify, we get this. That's at a minimum distance between prime numbers. The gap that will be formed is this equation. But as we go up, the average difference between prime numbers increases, so the gap increases more. As we go up on the prime numbers, we will get bigger and bigger gaps, while the prime tens proportion per length are limited by the factor pm minus 4 divided by pn. Also, the distance between flips of potential primes numbers increases. So this, you can start seeing that like all converges. Of course, this is in the cycles, not in the part that is the real composition of numbers. But the cycles through the gap are mapping the real composition of prime numbers, the real number line, right? The cycle of primes are mapping through their gap the real number line. At very similar cycles, with almost constant proportion of prime tens, the real numbers will look very similar to the cycles, with prime tens converging to the same distance of separation. We can see here how every cycle has a gap. We told this already. And how, at the same time, the cycles will be mapping the real number of line. But if all the cycles look similar, the real number will look similar to the cycles. This equation, that is the proportion of prime tens per length of cycles as Pn goes to infinity, together with this equation, makes me believe that there will be an infinite number of prime tens as we go infinity. But this is not a mathematical proof yet, because we needed to prove with equations. So how we prove that? And the way is to prove that with equations that the prime tens gonna fall in the gaps, that the gaps will always have prime tens on them. And for that we go for the next section. We have shown already that the cycle is going to be looking more similar to each other, but we want to prove with equation, as I said, the prime tens will be in the gap. So let's continue. So here we have the equations for prime tens per gap. That's what we need to try to prove that the prime tens gonna be in the gaps. We need equations for the prime tens in the gaps. Here we have number of prime tens divided by the length of the cycle is determined by this equation. This first term is for the cycle of 3, that it has only one prime ten by 30 of length of the cycle of 3. For every successive prime number, we're going to have cycles that they're going to be a factor of this term, right? So P2 will be prime number 7, and so on until Pn. And this whole equation determines the prime times per length of cycle. of the cycle. So for the equations of prime tens per gap, we're going to take this equation that is represented here, okay, times the length of the gap, because this represents all this equation. S minus 1 is the prime tens in the previous cycle, and L minus 1 is the is the length in the previous cycle. So if you multiply by Pm minus 4, you have the prime tens, and by Pm, you have the length. So this is the prime tens per length times the length of the gap. You're gonna have the amount of prime tens per gap. And now comes something tricky here, because I'm gonna make equations for the proportion of prime tens per gap for consecutive gaps. Consecutive gaps of the same separations of 2, 4, 6, 8, because we know all prime numbers are separated by the same distance. So the prime tens per gap, we're gonna call it a gap of +2 to the gaps that are formed by the difference of squares of prime numbers that have a separation of 2. And we're gonna call it gaps of +4 for for gaps that are formed by prime numbers with a separation of 4, right? So if we calculate this here, the 17 and 19, the gap created by these two primes, that will be a gap of +2. Gap of +2, because they are separated by that. If we calculate, for example, from the 23, 29, that will be a gap of +6, because the gap is formed by that separation of prime numbers. Okay, so remember this gap here, this gap here of +2 gonna be equal to 19 square minus 17 square. Okay, let's erase this just a moment. But we're gonna make equations for consecutive gaps of +2 and +4. For example, for consecutive gaps of +2, it's not possible, because you don't have 3 prime numbers in a row that has a separation of 2 between them. But it doesn't matter, we're gonna calculate that anyway, because we want to see how the equations behave. So for consecutive gaps, we're gonna have a separation of E, and this is gonna be an equation. For example, for consecutive gaps, the first gap, let's say we have prime numbers 17, 19, 21. That is not a prime number, but we're gonna calculate it like if it were a prime number, because the only purpose of this is to see how equations behave. So for this, we want to see how the proportion of prime tens change. So I'm gonna take the gap of these two and see the proportion of prime times in that gap, and then I'm gonna take the gap of these two, 19 and 21, and the gap from 19 to 21. I'm gonna create the gap, and I'm gonna see the proportion of prime terms there, and then I'm gonna divide this one here divided by this one here. So we gonna make a change. We're gonna see how they change if the separations of prime numbers are from 2 and 2, from 4 and 4, 6 and 6. Even that's not possible, right? But we're gonna do it to see how the equations behave. And that's why the equations we have there, because here we have, with an increment of e, we have one of the difference of squares of the first two prime numbers. If we start with Pn, the next prime number will Pm plus I. So if we subtract that, we have the gap. And this is the factor of prime terms per length, gap, that this whole thing gonna give us the prime terms per gap for a separation E. And for the next consecutive gap, then we're gonna have here Pm plus I now, because they are consecutive, right? And Pm plus 2I, okay? And this gonna be the length of the gap. But here we're gonna have a Pm minus 4 divided by Pm, but because we have another gap extra, we have to add another factor, and we have to add another I. So Pm minus 4 plus I and Pm plus I. It's the same factor, but in the next gap, okay? So we have this equation. Simplifying that equation gonna give us this equation here, okay? And that's gonna determine the prime terms, the change of prime terms per gap for two consecutive gaps. We're gonna see that now because I'm gonna make the calculations step by step, so be patient and we will see it in the next slide. Let's continue. So we're gonna work now with the gaps of +2. Remember that the gap of +2 are the gaps that are formed by the difference of squares of prime numbers that have a separation of 2. So first, we're gonna take Pn here and Pn plus 1. So Pn plus 2 is equal to Pn plus 1, right? So we have here the prime terms per length of the cycle. That is this one. That is the previous prime terms per length of the previous cycle times Pm minus 4 divided by Pm. And we're gonna multiply by the length of the gap. The length of the gap is Pm plus 1 squared minus Pn squared, and Pm plus 1 is equal to Pn plus 2. So we have Pn plus 2 here, Pn here. The difference of squares is the length of the gap. The length of the gap times the prime terms per length of the cycle times this gonna be the proportion of prime terms per gap for that specific gap, right? So if we simplify that, we get this equation. This is the equation simplified. And then second gap formed by the difference of squares of the prime numbers Pm plus 1 plus and Pm plus 2. Pm plus 1 and Pm plus 2. Remember that so Pn plus 2 equals a Pn plus 1 and Pn plus 1 equal no sorry plus 2 equals a Pn plus 2. So remember there is a separation between the primes of 2 always, okay? So here we're gonna have the difference of square of, we are putting everything in terms of Pn, of the original Pn of this. So Pn plus 2 is equal to Pn plus 4. So it's here. And Pn plus 1, we have here. The difference of squares between Pn plus 2 and Pn plus 1 is the length of the next gap, the consecutive gap after the gap that is formed by these two Pn's. And we multiply by the factor of prime times per length. This is the prime times per length of the previous gap, of this gap of Pn, the gap formed by Pn and Pn plus 1 is this one, right? So this one here. And we have to multiply by another factor because it's the next gap, and the next gap gonna be another factor like this, but remember Pn gonna be equal to Pn plus 2. So this here, it's really Pn plus 1 minus 4. And underneath is Pn plus 1. So that yields what? Pn plus 1 is Pn plus 2. So we're going to have here Pm plus 2 minus 4. And we're going to have here Pm plus 2. If we solve that, we have Pm minus 2 over Pm plus 2. So this here is this here, you see it? Okay. So we're gonna reach this equation here for the second gap. And now we're gonna divide the equation of prime times per gap of the first gap, okay, of the second gap divided by the first gap. So it's equation 15 divided by equation 14 is the prime times per gap. So we can see the change in prime times per gap, okay? So we have all this, and of course we're gonna cancel this out with this out, and this is gonna be canceled, and we're gonna reach and have this here, okay? This is gonna be the equation. So we can see that if we will have all consecutive prime numbers separated by 2, all of them, so 3, 5, 7, 9, 11, they are not prime numbers, but we are making like if they were prime numbers, so we can see what happened with the equations. But we see that this is gonna be less than, this one here gonna be less than 1, okay? So for consecutive gaps of prime numbers separated by 2, the prime times per gap gonna diminish Let's erase all this so you can see it again how it is, right? And we're gonna continue with the next slide to see the purpose of this. So here we have a table with hypothetic primes separated by 2, all of them. They are not prime numbers, most of them, but we are doing this to see how the equations behave. If the prime numbers were separated by 2, all of them, we will see that the size of the gap is going to be increasing, and the prime tens per gap will be decreasing all the way, okay? And this factor of prime tens per length of the cycle, how you see, it decreases also. And so that decrease doesn't help to find an easy way to prove that the prime times are gonna be in the gaps, right? So, but let's continue and see how the other gaps, the gaps of +4, +6, +10, how they do in this type of analysis. Let's continue. So we can see that the gap of +2, from gap to gap, consecutive gaps, or the prime tens per gap are gonna diminish. Also for the gaps of +4. But there is an inflection in the gaps of +6 because this is gonna be greater than 1. Okay? So the gap's gonna start increasing the number of prime times. And this also, the gaps of +10 also, and +8, of course, they're gonna increase. But you can see here that at big numbers, they converge, right? Because if Pn is very big in any of those equations, the change in prime times per gap gonna be less and less. The important thing is that when we have more gaps or more separation of prime tens of +6, +10, +8, and further, bigger separations, we're gonna have an increase of prime tens per gap. Okay, we're gonna see here that this factor is not the same as this factor. This factor converges more quickly. This is the prime tens per length. The change from one to another one converges more quickly. But this factor is the cumulative factors of all the primes on cycles of primes. And you can see that at the beginning, it decreases like this. It decreases not so quick. But if you have the same separations, but in the 10,000s, look how the rate of change decreases, right? Much more. Even these are not prime numbers necessarily, but it's the same separation as this one. We are looking how the equations behave, and that's important to have it in mind. I chose the gaps of +10, and we have here the separation from 10 to 10. Doesn't matter they are not prime numbers, we are seeing how the equations behave, and we can see that the factor decreases, the gap increases a lot, and how also the prime tens per gap start increasing. So they increase, and that's compared to the gaps of +2 that decreases. Now we have, because the separation between primes are of 10, the gaps that they produce, consecutive gaps, will increase the prime tens per gap. Okay? And here we are, the real prime numbers. Okay? We already calculated the prime number 3, and at the 7, this is going to be this factor here, right? Going to be like this with this number, and this is going to be the gap. that is the gap, look, is 121, that is the square of 11, minus 49, that is the square of 7, and that gives you 72. And this is the prime times per gap. And you can see how prime times per gap decreases here, increases, decreases, increases, and it starts increasing and decreasing because we have different separations of prime numbers. So we can see how this behaves, right? Uh, so the question is to know what are going to happen at infinity uh, if all the gaps going to start increasing. And that's what I'm going to prove, that when the PNs are greater and greater, the prime times per gap, they're going to increase always. And I'm going to explain why. But it will converge into a zero increase. But they're gonna go through the upper side, right? They will be always greater than 1, but converging to a 1-to-1 ratio in the proportion of prime times per gap. I don't know if you understand me. Let's continue. So now we ask ourselves why the prime times per gap increases or decreases. And the answer is that as longer is the gap, like for example here, it's a long gap, the more prime times gonna get from the cycle without the flips of the coming prime numbers of the coming cycles. So as the smaller is the gap, like here and here, small gaps, the sooner come the flips of the other prime numbers of the next cycles. So you now have less prime times per length. We know that once you have a cycle, the cycle doesn't have the flips of the coming prime numbers. So the longer the cycle, the more prime times you're gonna get, and the more prime times per gap you're gonna get. So that's the reason why it is increasing the number of prime times per gap when the gaps are longer and longer. What is happening is that when we calculate the prime times per gap, we have these two equations. These equations makes the prime times per gap increase. And this affects the prime times per gap also, that this decreases the amount of prime times per length, right? So when Pn goes bigger, this equation gonna dominate to the decrease of prime times due to these factors. Remember, this minus 4 in all factors makes less prime times per length, decreased prime times per length, right? But if the gap increases faster than the decrease of this equation, um, then this equation gonna dominate and prime times per gap gonna increase. Also that this equation is converging. As Pn is bigger, smaller is the change in distance between prime times, the increase in distance. So we're gonna find that as we go to infinity, prime times per gap gonna increase because this equation gonna dominate, and this is a divergent equation, and this equation gonna be converging and converging, and the change in prime times or the increase in distance in prime times gonna diminish. Okay. Now we're gonna study two gaps of +2, but with the separation of 10 units between them. So that will be, for example, if we have 31 and we are assuming that the next number will be 33, and then the next gap of plus 2 will be 41 and 43. Of course, 33 is not a prime number, but we are doing this to see how the equations behave, right? So these ones are separated by 31 and 41 are separated by 10 units. And we're gonna see, without taking account the gaps that will be produced between them, how the equation behaves. So just taking those numbers. Let's erase this. So in this case, we're gonna have that Pm plus 2 equal to Pm plus 1, and Pm plus 10 gonna be equal to Pm plus 2. Pm plus 2 is equal to Pm plus 3. You have it here, right? And the equations will behave like this. We solve first for the first gap, that the gap will be of a length of Pm plus 2 square minus Pm square, and we solve it. And then we solve for the second gap here, that will be Pm plus 12 square minus Pm plus 10 square. And we'll have this equation as a result. And now we can see that this is gonna be greater than 1 when we make the division between the proportion between this divided by this, and we have this, and we get this, and we see that the proportion gonna be greater than 1, right? So, and there are two gaps of plus 2, so that tells us that depends what is in the middle of those gaps of plus 2 if gonna be increasing or decreasing the prime tens per gap. And that's very important because we have studied consecutive gaps of plus 2, plus 4, and all of them are plus 2, all of them are plus 4, and now we are studying different combinations of gaps between them. Okay, we're gonna see that the gaps of plus 2, they from one gap of plus 2 to another gap of plus 2 could be an increase in prime tens per gap due to the other gaps that are in between them. Okay, let's continue. And here we have an example. We make a table, and these are prime numbers, but here are fictitious prime numbers, fictitious separations. If we calculate the factor is here, starting from the cycle of 3 and 7, we calculate these factors, right? We have it here, and we see it's decreasing like always, and the prime tens per gap, we can have it here. And now look, we have a gap of plus 2 here in 55 and in 109. They are fictitious, but we are watching how equations behave. And from this one to this one, there is an increase from 0.3 to 0.45, because the separation of primes between them are of here of plus 10, plus 20, plus 6, and plus 6 again. So because this gap, these gaps, these prime numbers that are going to form gaps, then now there is an increase from one gap of plus 2 to the next gap of plus 2. So This is because this factor is cumulative and affects the prime times per gap to all gaps, to subsequent gaps, right? We're gonna see the next slide. To better understand it, let's take a distance of 100 and compare the evolution of the factor pm minus 4 over pm versus the evolution of the length of the gaps through different compositions of primes within these 100 units. Let's say one composition consists of primes separated by short distances and another by large distances. We will designate them based on their prime separations, such as +2, +4, +6, +10, +26. And these separations will add up to 100. First composition is this one. You see there is small separations, +2, +4, +2, +10, for a total of 100. And the second composition are gaps formed by separations of the primes of +14, +10, +26, +22, +28. Again, for a total of 100. So these will be the separations of the prime number. This +2, +4 here, +2, +10. And we can see that this is gonna add 100. And so you're gonna have a lot of factors of this. You're gonna have for each separation, you're gonna have one factor of this. So you're gonna have multiple factors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You're gonna have 18 factors of this. Every time you have one factor of this, the separation of prime tens increases, right? Because more prime tens are flipped. And here, because the bigger separations, you have only 4 factors. 1, 2, 3, 4, 5. 5 factors. So here you're gonna have less separation of prime tens, because for the same distance, for 100, you have less factors, so you're gonna have less, much less prime tens flip than in this one up here. Okay. Here, this slide and the next slide are the cycle of 3 and 7, the second iteration, and the third iteration of the cycle of 3 and 7. This is the second one, this is the third iteration. And we can see that for gaps of +2, consecutive gaps of +2, they are not consecutive, the one and the next one. For example, in 221 is 0.384, and we can see that the next one will be in 227, the next gap of +2, and gonna be 0.3806. So there is a decrease. And gaps of +4 also 0.76 in 223, and here in the 229 we have another gap of +4, and it's 0.757. There is a decrease. But then there are gonna be increases. This is a gap of +6, and if you compare with the next gap of +6 that is here, there is an increase from this one to this one. So they're gonna fluctuate. Some gonna increase, someone's gonna decrease. Depends if +2 or +4. Remember that in the cycle of 3 and 7, we are taking account only the multiples of 3 and 7. We are not taking account any other prime numbers. But what it increases always is the corresponding gaps from one iteration to the other iteration. This is the first gap of the second iteration, and this is the first gap of the third iteration. And you can see that from one to the other, in a gap plus 2, there is an increase. And from here, this one, second gap, there is an increase. And this one, 0.0380, increased to 0.40. And when you reach the last gap of that is in the next slide, uh, you're gonna have also an increase. So overall, you're gonna have an increase. And as Pn goes bigger and bigger, remember that this equation is gonna be converging to a 1-to-1 ratio. So what we know is that you're gonna never gonna have a decrease of prime tens per gap that's gonna go to 0. No, you're gonna approach 1, and when the next coming prime cycles comes, the separation between primes is gonna be bigger and bigger. There are gonna be more separation zones, and there's gonna be a moment that the increase will be in all gaps. All gaps from +2 to +2, there's gonna be an increase. +4 to +4, there's gonna be increase in all the gaps. Remember that when I say increases from one gap formed by the same separation of prime numbers, gap +2 to the next gap +2, gap +4 to the next gap +4, gap of +10 to the next gap of +10. And there's going to be a moment that those changes going to be always an increase with approach to convergence of 1-to-1 ratio. Because all the coming cycles are repetitions of the cycle of 3 and 7, and really the cycle of 3. But they are repetitions of the cycle of 3 and 7. You know that this never gonna decrease. The prime tens per gap never gonna decrease, and they don't decrease from one gap to the other one. They decrease here from in the same iteration, but from one iteration to the next one doesn't decrease. It always increases. So eventually, as I said, we're gonna have an increase in every gap of any size, gaps of any size. Gaps are gonna get bigger and bigger, and they're gonna be always an increase. So here we have the last gap of the iterations, and we can see that there is the prime times per gap gonna increase from the second iteration to the third iteration. So there's gonna be always an increase for the coming iterations. And remember that the coming cycles of other prime numbers, they only gonna separate more the prime terms, so gonna produce more of an increase. So we are guaranteed that we don't gonna have a decrease in prime terms per gap, a continuous decrease. We're gonna have a continuous increase. Look that from one gap to from one iteration to the other one, there is always, sorry, from here to here, here to here, there's always an increase. Doesn't matter that there is a decrease from gaps of 2, for example, here to the next gap of 2 that will be here. So 11, 39, 38, that's a decrease from the one gap of +2 to the next gap of +2. But from one iteration to the other one, there is always an increase. Remember that because the last ones, there is an increase in the last ones, for every iteration of the cycle of 3 and 7, there will be always an increase. We're not gonna get a decrease that we're gonna go approaching 0. This is gonna approach 1. All of them gonna be approaching 1. We have here the second iteration. And here we're gonna have, this is gonna be the, sorry, this is gonna be the third iteration. per iteration. So we are clear, okay? When the next cycles comes, they're gonna get bigger and bigger, the separations between primes, so the gap's gonna be bigger and the proportion of prime tens gonna increase. So we know that as bigger are the separation between the prime numbers, the bigger gonna be the gaps, and the bigger gonna be the prime tens per gap. They're gonna increase the prime tens per gap. And here we have a big separation between prime numbers. These are already into the billions of numbers, and these are all prime numbers. So look, from 207 goes to 223. That's 16 of separation. And from 223 to 241, 18 of separation. And this one goes to 271, 30, separation of 30. There is even huge separations. Look, this one here, for example, that's 663 to 711. That's another big separation. There is even separations of hundreds. So at those big separations already in the billions, the prime tens per gap are going to increase. We can do more computations. I have done computations, and the prime ten per gap increase always from gap to gap, from the gap of +2 to the next gap of +2, from a prime 10, all the separation of a prime 10 to the next prime 10 gonna be an increase. So you're gonna have increases all the time. So the prime 10s per gap increases and continue increases, even at a huge number is going to converge and going to go converge into a proportion of 1 to 1, right? To a zero increase. But they're going to increase a little bit always, okay? It's a converging process. So here we have this graph again, and let's imagine that we have no prime tens in gap 1. We know that the proportion of prime tens in gap 1 gonna be the average of all the prime tens in the cycle, in cycle 1, divided by the length of cycle 1. So there's gonna be a proportion there. But imagine, because the prime numbers doesn't behave at the small scales like the gaps are constantly, imagine it happens that there is no prime tens there. So then comes gap 2, and you can say the same argument. Gap 2 has a proportion of prime tens that is equal to the length of to the number of prime tens in the cycle 2 divided by the length of cycle 2. And so imagine there is no prime tens there because they are on other parts of the cycle. And you can say the same thing for the gap 3 and gap 4, gap 5. So how are you going to prove that they're going to appear, the prime tens in the gaps? And it's the following analysis. It's the segments analysis. When you have a gap 1 and you don't have prime tens, then comes gap 2. But gap 2 is formed by the next segment of the cycle of gap 1, but with additional flips of the prime number that forms the cycle that the gap 2 belongs to, right? So because in gap 1 there was no prime tens, the next segment that is tied to the gap 2 gonna be more prone to have prime tens there, because if they were not here in gap 1, gotta be more in the rest of the cycle to fit the proportion. And when it comes gap 3, happens the same, gonna be formed by the segment of gap 2 and next segment of gap 1 with additional flips of the cycle of gap 3. done by the prime number that merges in the cycle of gap 3 of this cycle. And the same will happen with gap 4. So there's gonna be a moment that they're gonna be forced to appear because the prime terms per gap are increasing and converges to a constant. So in some segments gotta appear the parts of the cycles that have more prime tens. And eventually the flips inside the gaps gonna be less than the number of prime terms in the gap. The flips of prime terms in the gap gonna be less. That's also a study in the paperwork, but because the separation of flips is bigger and bigger. And you're gonna have multiple prime terms per gap, so you're not gonna have enough flips to flip all the prime tens. You're gonna have 3, 4, 20, 100 prime tens per gap because the gap is a diverging equation that keeps growing and gets bigger and bigger. So this with the equations that the prime tens per gap do not diminish, that they converge to 1 and they increase. For me, we're proving the twin prime theorem. We're proving that there is going to be always prime tens in the gap as we go to infinity. So as a conclusion, we have here that we are approaching an ideally full prime tens cycle for similar repetitions of previous cycles. So this makes also already a conceptual approach to a solution, right? But with the equations, we have that the prime terms, when we add the effect of all gaps and the equation of all gaps that are assumed in this one, this equation, we arrive to the conclusion that the prime terms per gap are gonna increase as Pn increases, and that increase is gonna be diminishing and converging to a zero increase, but they always increase. They will never diminish the prime tens per gap in the gaps, right? And these two equations that are the prime tens per length of the cycle versus the length of the cycle, we find by the equations that this is gonna dominate and that there are gonna be an increase in prime tens per gap. Altogether, with the analysis of the segments and how the prime tens are forced to be in the gaps, prime tens will never decrease in the gaps for an infinite number of prime tens. So we have shown that the prime tens are forced to appear in the gaps because all gaps are linked to each other, and they don't diminish in prime tens per gap, and they will be forced to appear prime tens per gap to hold the equations. If not, the equations will not be like this, right? So thank you for watching. That will be all. In the paperwork is better written and has more information. Thank you for watching. I hope to have comments from you. Give me your opinion and see you soon. Thank you. My name is Manuel P. Rodriguez Velasco. Thanks for watching.